So in this video, we talk about fragmentation and assembly. So here's the basic problem that fragmentation and assembly try to solve. Let's say that myth, I'm using some machine at Stanford in the myth cluster, and I want to request a web page from Google. And Google's web page that it sends, this HTTP response, is 10 kilobytes long. Well, a 10 kilobyte chunk of data is pretty big. And the problem is that there might be some hop along the path from Google to myth that can't support a 10 kilobyte packet. In fact, Ethernet, the maximum transfer unit, many speeds of Ethernet support, is 1500 bytes. And so what I need to do is take this 10 kilobyte packet and break it into a series of chunks, smaller pieces called fragments, which the network can support. So imagine like the extreme case, if I'm downloading something really big, I don't want to be sending 1 gigabyte packets. They're going to occupy the channel for huge amounts of time. So I want to break things into smaller chunks. So in this case, if I had, say, an Ethernet frame size of 1.5 kilobytes, I'll need to split this 10 kilobytes into seven fragments, where these first 6 could be 1.5 each, and the last one, say, is 1 kilobyte. So that's the process of fragmentation. Then these fragments arrive at myth, and its job is to assemble, and it's assembly. So to take these 7 fragments, 2, 3, 4, 5, 6, 7, and reassemble them into the original 10 kilobytes of data. And so generally speaking, fragmentation and assembly occur when a higher layer's data unit is larger than what a lower layer can support. It's a fragmentation, the process of taking a large chunk of data and breaking it into smaller pieces that the lower layer can support. And assembly is in the process of taking these fragments and reassembling them into the original data. This occurs in many different places in networks at different layers. For example, it can occur at the transport layer. So TCP does this when it takes a stream of data, it breaks it into segments, which are then transmitted and reassembled at the other side into a reliable stream. And this assembly is now occurring end-to-end between the two TCP endpoints, such that a given TCP segment, once it's generated by an endpoint, is then indivisible and arrives at the other end. You never see a segment broken into 2 separate segments, although underneath it might be broken into packets or frames, as I'll show. Contrast the network layer, it's operating on a host-to-host basis. This is unlike TCP, where once a segment is sent, that is the segment the endpoint will receive if it arrives. With IP, at the network layer, it's possible that some intermediate node takes the packet and breaks it up. So an RP packet traversing the network at some intermediate point might be broken into multiple IP fragments, which then the endpoint has to reassemble into the original IP packet. And so this is at the network layer, and so it can occur within the network. Finally, it can also occur at the link layer. So one example is there's a link layer called Zigbee or 802.15.4 that has a very small frame size of approximately 120 bytes, 127, but that doesn't, you have to include the header in that. And there are times when you want to send large packets on this frame size, like an IPv6 packet, which can be 1280 bytes. And so what happens is that the IP layer passes a 1280 byte packet to 6LoWPAN, called IPv6 Low Power Personal Area Network. It's to link layer support for IPv6. And 6LoWPAN at the link layer breaks it up into fragments, which are then sent over the link, reassembled at the other end of the link into an original packet. So in this case, the fragments are purely on the link, and the network layer doesn't see it. In the IP case, the network layer sees it. In the transport case, transport layer sees it, but the actual transport segments are not broken. So let's walk through a concrete example. So the one of the really common cases of fragmentation, or rather it's not common, people try to avoid it, but it's a very simple mechanism, so it's good to explain, is how fragmentation works in IP, in the Internet Protocol. So here, let's imagine we have a route between across 3 hops, where the first and third hops use Ethernet with a maximum transfer unit of 1500 bytes, but the middle hop uses a point-to-point link with a maximum transfer unit of 576 bytes. This means that at the link layer, the frames can only support, say, 576 bytes of data or 1500 bytes of data in their payload. So what happens now is some application at the host on the left wants to send a 1400 byte payload. And so on the first hop, this is fine. We can take a 1400 byte payload, and IP header is 20 bytes. And so we have 1420 bytes. We can then put that in Ethernet frame. 1420 fits just fine inside Ethernet. But what happens when we hit the second host? We can't take this 1400 byte payload and put it into a PPP frame because it won't fit. So what IP does is it takes the original packet and splits it into 3 fragments. So this is something which is going to occur here at this node. This node is going to receive an IP packet with a 1400 byte payload in this given IP header. Then realizing it should go out over this PPP link, will take it and generate 3 separate IP packets. I'll show how they're formatted in a minute, as separate PPP frames with smaller payloads. So in this case, say 512, 512, and 376 bytes. But so the trick though is that once this packet has been fragmented at this second node, those fragments then pass through the network unchanged. So the third node here does not reassemble them. Instead, what's going to happen is that it's going to just forward them along and put these 3 IP fragments inside Ethernet frames and forward them along to the destination. And then hopefully the destination will receive all of them and reassemble the original data of 1400 bytes. So how does this work? So if we look at an IP header, there are a couple fields in it which allow this to happen. So basically there's the ident field in an IP packet here. And the ident field is what allows the fragmentation assembly layer in IP, or the fragmentation assembly in IP, to be able to tell whether or not these are fragments of the same original packet. So before fragmentation, we're going to see a packet that looks like this, where its ident is, say, some value x. And remember here, this is the more fragment bit of the IP header. This was 0 here. This is the more fragment bit. And there's the offset field. It's this original packet. This is a standard IP packet. It's just an identifier. There are no fragments. There's an offset of 0, and it's just a 1400 byte fragment. But then after the packet is fragmented, the more fragment bit is set for all but the last fragment. So here, this first fragment here and the second fragment both have the more fragment bit set to indicate that more fragments are coming. The last one does not. And then the offset field tells a receiver where this data begins. And so as we can see here, this is a 512 bytes of payload. And so this goes from offset 0 to 511. Now this second fragment is going to start at byte 512 and it goes from byte 512 to 1024. And so the offset field is what indicates this. So the offset field is not in terms of bytes, but rather in 8-byte chunks. And so 64 times 8 is 512. And so this tells the receiver that this second fragment occurs at offset 512 within the packet. This is at offset 0, and then this is, of course, at offset 1024. The ident field is identical in all 3 fragments, and so this means that now an endpoint receiving these 3 fragments can properly reassemble the original IP datagram. And so the combination of the ident field and the source address is what allows it to cluster these 3 fragments together. And now since the offset field is encoded in 8-byte chunks, that means that each of these chunks, these fragments, must be a multiple of 8 bytes long, except for the last one. So fragmentation is, in the IP case, really helpful because it means that an endpoint can generate an IP packet without having to worry about what the intermediate maximum transfer units of the links are. So it's a great way for an endpoint to be able to generate packets without having to know properties of the entire path, especially if, say, the path is dynamic. That being said, in practice, systems really try to avoid IP fragmentation. And the reason is that you've suddenly taken one packet and made it into multiple packets. And it's now the chances that any one of those packets might be dropped goes up. If, say, let's say 1% of all packets are dropped, suddenly you're increasing the probability that one of those 3 and therefore will be dropped, and therefore the whole original packet will have to be lost. IP doesn't support any reliability or retransmission of these fragments, so if one fragment is lost, generally you have to retransmit all of them, and that's up to a higher layer. So generally you want to avoid IP fragmentation. So one interesting trick that, or approach that TCP sometimes uses is to actually choose a segment size to avoid fragmentation. Since TCP segments can be of any size that TCP wants, what it does is it tries to generate segments which will fit inside IP packets and not fragment on the path to the destination. And the way you can do this is by setting the don't fragment bit. And so say a TCP connection, when it opens up, it can say, choose, well, I'm going to try sending, let's just say a standard Ethernet frame of 1500 bytes. I'm going to set the don't fragment bit. And if it gets an ICMP error saying, oh, couldn't, this thing couldn't, I had to fragment it and I couldn't, then it says, I'll try something else. There must be some smaller, like, I'll see if maybe there's a 512 byte PPP link. And there's a bunch of ways you can search for this. One is to do a binary search. That's expensive. You can also just try common sizes like 1500 bytes. There's an RFC that talks about the options. But this is an approach where TCP can actually sense the connection, sense the properties of the path for a connection, and based on that, pick an optimal segment size such that it doesn't have fragmentation, but it's also able to minimize header overhead. It has as much payload per header, given that it's minimizing the number of segments that it sends.